Question number 2. Figure 1 shows apparatus used in an experiment to determine the enthalpy of combustion of leaf alcohol. So what's the heat change, how much heat is given out when leaf alcohol is combusted, burnt, reacted with oxygen. So what have I got? I've got a 50-gram sample of water, I've got leaf alcohol in a burner, I've got the mass of the spirit burner before and afterwards, and I've got the the temperature of the water before and afterwards. First of all, however, it's asking to write an equation for the complete combustion of leaf alcohol. So it's given me the formula again of the leaf alcohol. So what's it got? It's got 6 C's, it's got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 H's and an O. So I've got C6H12O, or you could put C6H11OH at the end if you wanted to. I've got oxygen as well that I'm going to combust it in, and it says complete combustion, so it's going to make carbon dioxide, CO2 and water as well. Incomplete combustion would make carbon monoxide, CO, or if it said it made a black solid, it would make C, carbon. But this says complete combustion, so that means that I'm going to make CO2 and water. So first of all, I've got C6H11OH, or I could write it as C6H12O if I wanted to. Either is acceptable. I've got oxygen because that's what I'm combusting it in. Combustion is a reaction with oxygen. I've got CO2 and water because that's what happens when you get complete combustion. Rather than CO and water or C and water if there's incomplete combustion. CO2 and water, I've put 6's in, that's easy enough. 6 C's there, the only place that the C's go are here, so I must have 6 C's here. I've got 12 H's, 6 times 2 is 12 for the H's, and the H's are appearing here. Let's add up the number of oxygens then, that's the final step. 6 times 2 is 12, 6 times 1 is 6, 12 add 6 is 18 O's. I need 18 O's here. Well, let's not forget this one, I've got 1 here, so I must have 17 O's here. So I want a number here that multiplied by 2 gives 17. So the answer is going to be 8.5. 8.5 oxygens. Let's just check again. 6 C's, 6 C's, 12 H's, 6 times 2 is 12 H's. 1 add 8.5 times 2 is 17, 18 O's there. 6 times 2 is 12, add 6 times 1 is 6. Yes, my oxygens balance as well. So what am I going to do with this question? Well, let's have a look at the next one. I've been given specific heat capacity here. The only reason I've been given specific heat capacity is to have delta H, sometimes known as Q as well. Delta H or Q, the heat change equals minus MC delta T. Delta T, triangle T, is temperature change. So I've got my heat change equals minus MC triangle T, temperature change. M is the mass of the water that I'm heating up there. C is my specific heat capacity, 4.18, and my temperature change are these two taken away. I ignore the mass of the spirit burner and the alcohol that's being released. I don't use that. M is the mass of the water that's being heated up and changed. So ignore these figures for now. So what have I got? I've got delta H, heat change, or Q, is minus 50 multiplied by 4.18, which is the specific heat capacity, multiplied by the temperature change. So my first job is to get the temperature change. It's gone from 20.7 to 40.8. It's gone up by 20.1. So my temperature range is 20.1, and then Q, or delta H, heat change, is minus, there should be a minus in there actually, minus 50 multiplied by 4.18, that's the mass. 50 is the mass of the water that I'm heating up there. Minus 50 multiplied by 4.18, multiply, which is specific heat capacity, multiplied by triangle T, delta T, temperature change 20.1, 4201, and it's measured in joules because specific heat capacity is in joules per Kelvin per gram. It's got a J there, so that's in joules. You convert it to kilojoules if you want. Does it say it's got to be in kilojoules? No, it doesn't, as long as you've got the unit, so you can leave it in joules if you want, or you can convert to kilojoules. I'll show you that in a minute. 4201 joules is what it's measured in. And that's fine. That should be a minus actually, because it's a minus MC delta T. It's exothermic anyway, so that would mean it would be a minus. Let's have a look what's next then. So my next thing to do is to have a look at the mass of alcohol that's burnt, because that value should be per mole of alcohol that's burnt. Well, let's subtract those two. 56.38 minus 54.84 will give me the mass of alcohol burnt, and that's 0.54 grams. I've got the MR of the alcohol. I can work out the MR of the leaf alcohol. It doesn't tell me in the question, but that's my leaf alcohol, C6H11OH. So I've got 6 times 12 for the carbons, 11 times 1 for the hydrogens, 16 then there's times 1, there's 1 of those, and 1 for the H, and that will give me an MR of 100. So I know how much alcohol is burnt, 0.54 grams, by subtraction from those two. I know the MR of the alcohol. Why would I be given mass and MR to work out the number of moles? Moles of alcohol is 0.54 grams divided by the MR 100. I've got 0.0054 moles. So let's just have a look what we've got. We've got 0.0054 moles of alcohol releases 4,201 joules of energy. I need to know how many joules of energy would be released if I had 1 mole, not this small amount here, but 1 mole. So if that small amount, 0.0054, releases 4,201 joules, 1 mole, a larger amount, would release more energy. How do I scale up? Well, I take that number and I do 1 divided by that. So 1 divided by 0.054 is going to give me a number to scale up by. 1 divided by 0.054 multiplied by 4201 will give me the number, the amount of heat change, if I had 1 mole. Let's just check my calculation again. That's a small amount giving a small amount of joules. 1 mole would give a larger number of joules. 1 divided by 0.0054 is my number to scale up by, multiplied by 4,201 gives a much larger number of joules. Yes, that's correct, for a larger number of moles, 1 mole of alcohol. 778,000 joules per mole, mole to the minus 1 means for 1 mole, and that's your answer there. If you wanted to divide by 1,000 and work it out as kilojoules per mole, you could do, but it doesn't tell you to do so. In this case, it's allowing either. State how your answer is likely to differ from the value quoted in reference sources. Well, look at this experiment. We're measuring the temperature of this. We're going to assume that the heat from this alcohol actually heats up all of that water in the beaker. It might not. I might get heat loss. So that's one answer. I might actually not fully combust some of the alcohol. Some of it might evaporate. I might not get full combustion, a full reaction of the alcohol. Some of it might evaporate. And I'll actually heat up the beaker as well. So the beaker will get hot and the water may not. So all of those are possible answers, although your main answer is going to be heat loss. Heat loss is going to be your main reason, although other answers are possible as well, incomplete combustion or heat transfer to the beaker and not the water. Oh, and let's have a look how it's going to differ. There's a mark for saying that it's less negative. How does that work out? Less negative. A smaller negative number. That's because not all of the heat will be measured. Some of it will be lost, and so it won't measure as much as large a temperature rise rather, so that number will be smaller. 20.1 will be smaller. You won't see the full temperature rise because some of the heat will be lost, and so you'll get a smaller temperature rise in there. 20.1 will be a smaller number, and so this will be a smaller number. It will be less negative. It might be something like minus 600,000 joules instead.